The topic that we are going to cover today is electric potential at axial point of electric dipole. Now, electric dipole, we studied about this in the first chapter, that electric dipole is two equal and opposite charges separated by some small distance. So this is your dipole. Two charges minus q plus q separated by distance of 2L. This O is the center of dipole. Why we used to take 2L? We used to take 2L because it makes more simpler to solve when we take 2L. Now you have to find potential at axial point. The axial point remains same. Axial point means the point at axis. So this is the axis of dipole. So I've taken a point P over here on which I have to find electric potential. Now let us say distance of this point from center is R, as you can see. So from plus Q, distance of P point would be R minus L, and from minus Q, it would be R plus L, as you can see the diagram. Now at this point, at point P, the potential is due to two charges, plus Q and minus Q. So I've given the symbol over here. Let V1 be the electric potential due to minus Q and V2 be the electric potential due to plus Q. I hope the diagrams and symbols are clear to you. Now let's move forward. Now we have to calculate V1 and V2. In the last video, we discussed about potential due to a point charge. What was the formula? The formula was KQ by R. So if I want to find V1, let us say V1, the formula would be KQ by R. So this is K, but Q is minus. V1 is due to minus Q, and you cannot ignore minus sign. KQ by R. Distance from minus Q is R plus L. So let us say R plus L and minus sign. Now why you cannot ignore negative sign here? Because there might be question in someone's mind, because when we were doing electric field intensity at axial point, we were not taking the nature of charge. We were not using negative sign for that. Now see, potential is a scalar quantity, whereas electric field intensity was vector quantity. So in scalar quantity, sign plays a role, but in vector it does not. Because of the sign in vector quantity, you were finding the directions. So when you find direction, the role of sign is over. But in scalar quantity, as they do not have direction, so negative charge or the negative nature would play the part. That's why. So V1 is minus KQ by R. V2 is KQ by R only, but distance is different. So it would be KQ divided by R minus L. KQ divided by R minus L. So we have to find total potential. Now, as it is a scalar quantity, we don't have direction. So it will follow scalar law of addition. And scalar law of addition is to add all the individual potentials, V1 plus V2. Now, why I'm adding? Suppose there are two wires which merge into one. One wire has electric current of 5 ampere. Second has current of 2 ampere. So that in single wire, what would be total value of current? Answer would be 7 ampere. So you just add up. So in scalar quantities, to find net effect, we just simply add them. So to find electric potential, we are adding them, V1 plus V2. Now put the values. V1 is KQ by R plus L. Minus is here. Plus KQ by R minus L. So we now just have to solve it. Take the common. We'll take the common. And if I take the common, what is common? KQ is common. Right? Now, what you are left with in bracket? You are left with 1 upon R minus L minus 1 upon R plus L. Take the LCM. Now, if you take the LCM, what you get in denominator, you will be getting A plus B, A minus B. That is A square minus B square. That is R square minus L square and bracket R plus L minus R plus L. This you get when you solve the LCM. So R and R cancel. L and L, 2L. So what you get in numerator? You get 2K, Q and L divided by R square minus L square. Now if you remember dipole part, there was a formula which was Q into 2L. That was the dipole moment. So this can be written as K. This part 2QL becomes P. That is dipole moment. Kp divided by R square minus L square. So this is the formula of potential at axial point. Now if dipole is very small, that means L square would be neglected. So the final answer for short dipole would be V is equal to Kp by R square. This is the final formula of electric potential at axial point of dipole.